Hi, this is Linhao Zhang. So the name of the paper is Classification of Imbalanced Data by Oversampling in Kernel Space of Support Vector Machines. Next page. Okay. So this paper focuses on the imbalanced classification in industrial datasets. The imbalanced dataset has a positive minority class instances, and this will affect classifier and the error matrix to have a bias towards the majority class. For industrial dataset, it may need a nonlinear model to classify multiple classes. Previous method that handle imbalance classification includes oversampling method, like randomly duplicate minority instances. Cost-sensitive method, the example of this will be like to have a larger penalty on misclassified minority cases. And also many other algorithms like support vector machines can handle imbalanced data. The solution proposed by this paper is a weighted kernel-based mode algorithm. Usually, mode algorithm oversample random minority instances in the input space and then maps instance to a feature space. But weighted kernel-based mode oversample the minority instances directly in the feature space of SVM. The paper also mentioned that this mode algorithm can be replaced by other oversampling algorithm as long as we use feature space distance function to find nearest neighbors. The second part of this is that unlike other algorithms that gave equally weight to minority instances and synthetic instances, this algorithm assigns different weights to minority, majority, and synthetic instances. The paper also introduced a hierarchical classifier framework. The idea is to divide the dataset into a sequence of binary classification subproblems, and the weighted kernel-based mode synthetically balance the minority class at each subproblem. Then the paper introduced simulation experiments. It uses a G-mean assessment metric, which will close to 1 if all classes were correctly classified, and also a fragment test. So researchers compare the weighted kernel-based mode with other 9 baseline algorithms. The gray search was used to optimize the G-mean score, and they also use 3 different ways to set classes weights. So first, they simulate a 2D toy dataset. Minority instances are represented by blue squares. We can see from the figure 4 that weighted kernel-based mode has a more clear boundary than other algorithms, and it has less overlap on majority instances. Second, they simulate a 3x3 grid that minority instances are at corner regions. And we can see that in the plot, the weighted kernel-based mode algorithm has a better grid boundary than others. Then researchers apply this algorithm to 51 binary datasets, record their average G-mean score. So here is the part of the result. We can see from the table that WK mode, which is the last column, has the maximum G-mean score on many datasets. The next part of the paper is the application of weighted kernel-based mode on an industrial PD dataset, which has 7 features and 3 class labels. For this dataset, researchers apply the hierarchical framework. The first level classifier treats stage 2 and stage 3 as a single class. The second level classifier will build classification between stage 2 and stage 3. So we can see from the results that weighted kernel base mode, which is the last row, has the highest Gini score. So what can we use for our project? Our group are working on financial data set that data is highly imbalanced. This paper explained different methods like small SVM and also cost-sensitive method in very detail. And the weighted kernel-based mode take advantages from all three different methods. So we can try to apply these algorithms to our data set and see if it can improve the performance model or not. And here's the reference. Thank you. That's the end of my paper review.